We are Group 7. Our group consists of Alan Chavira, Miguel Corral, Jose Duran, Colt Pauly, and Ignacio Reyes. We will be going over the integration, verification, validation, and test plan of our see-through chip tracker projects. These are the STCT IVVT activities the plan consists of. We will be going over the system overview, different VVT evaluation tools, the different IVVT activities we applied in the definition, design, implementation, integration, qualification, and post-development lifecycle phases of our projects. We will also go over the project's conclusion and discussion. The purpose of the IVVT plan is to assess the potential risk of the system and identify the appropriate IVVT activities to manage those risks and compliance to the specific stakeholder and system requirements. This document specifies the different IVVT methods that will be applied in order to evaluate the system's performance. The IVVT plan details what, how, and by whom the activities will be performed. The plan includes detailed explanation of the techniques that were used to prioritize these activities. These documents will be reviewed by the IVVT team to ensure that the requirements are correct and are being met. We identified the VVT strategies and activities that needed to be performed to optimize testing and to ensure that that unnecessary and irrelevant tests were not performed. This document applies exclusively to the see-through chip tracker system.
So practically all new autonomous vehicles use visual sensors to determine where they are as well as where they are going. These visual sensors can detect road signs, traffic lights, and medians with surprising accuracy. However, a flaw does reside within this form of visual sensing. If the road signs, traffic lights, or medians are impaired by damage of some sort or visually obstructed for whatever reason, the autonomous vehicle is now driving blind. The plan for the STCT is to put special RFID chips on all major road signs, traffic lights, and medians in the United States. These chips would send a special signal to a new type of receiver on the vehicle, telling it exactly what road sign, stop sign, yield sign, street sign it is, what side of the road the vehicle is on, and what type of traffic light is approaching, whether it be green, yellow, or red.
The key personnel are Alan Chavira, Miguel Corral, Jose Duran, Colt Potley, and Ignacio Reyes. We exchanged our UTIP emails and created a VVT group on the Microsoft Teams, which was our main point of communication and where we uploaded the project's documents. Our group meetings were on Wednesdays at 7 p.m., and if necessary, we either met on Thursdays at 7 p.m., Saturdays at 12 p.m., or Sundays at 12 p.m. Meetings usually lasted between 1 and 2 hours, and a few times it lasted between 3 or 4 hours, depending on the IVVT activities. Here are the relevant acronyms we use throughout our IVVT plan. The main ones we'll use in the presentation are see-through chip tracker, verification, validation, and testing, concept of operations, cost-benefit analysis, requirement verification matrix, requirement bidirectional matrix, and built-in test. The organization and team responsibilities are the following. Colt Pauly is the team leader. He ensures the project VVT team are meeting the goals of the STCT project. Miguel Corral is the planning manager. He defines the goals and determines the missions that will be necessary to achieve the project's set goals. Alan Chavira is the process manager. He plans and monitors the performance of the project's processes throughout its life cycles. Ignacio Reyes is a quality manager. He oversees that all VVT activities and tasks are maintaining the desired level of excellence. Jose Duran is a support manager. He coordinates technical information of the STCT and educates the team members on how to use it. Each team member is responsible for executing their tasks and assignments, getting them approved, and keeping the VVT team and stakeholders informed. In this master schedule Gantt chart, we have the IVVT activities and milestones, their corresponding module, their start date, and their due date. Our project lasted 14 weeks where we conducted 23 different IVVT activities and events throughout 7 modules. Each module activity and event are color-coded, and they are identified in the key chart. Most module IVVT activities lasted 1 week to complete. Previews lasted between 3 days and 1 week to analyze, document, and implement the corresponding updates. Each IVVT plan documentation update lasted between 1 and 2 weeks to implement the corresponding modules IVVT activities. The project checklist and defect logs were conducted after each IVVT activity, preview, and IVVT plan documentation update of the project.
5.1 Risk Management. Risk was evaluated in 2 factors: probability of occurrence and impact. These factors are then multiplied to assign an overall risk score. Criteria is defined as decisions taken and actions required depending on the risk exposure. In our case, the scores range between 1 and 100. From 1 to 25, we have decided to accept the risk. 26 to 70, we have decided to mitigate. Over 70, we have decided to mitigate and have a contingency plan. We have identified that only requirement 3.3 requires a mitigation plan due to the high risk score. 5.2 Checklist and defect log. Each requirement was evaluated individually using a predefined checklist. This is performed to ensure the requirements are unambiguous, consistent, complete, needed, feasible, traceable, and verifiable. When a requirement does not meet the criteria, it can spiral into different interpretations, cause confusion, be an unmeetable requirement, or worse, down the line, they can cause unnecessary cost. 5.2 Checklist and defect log. Now that all the requirements have been evaluated, any changes will be recorded using a defect log. This is used to maintain traceability of changes, reason, when the defect was first introduced, and the stage where it was removed. The time to correct the defect is also recorded. This helps track the cost of rework. The defect log can also be used in other documents as a review and tracking tool.
In our project start RVM, we included the requirement number, traceability ID, the system's requirements, and the category they fall under, such as functionality, performance, and maintainability. The verification method technique used, the lifecycle stage they take place in, and it will be applied to a specific component, subsystem, or the whole system. There are various verification method techniques shown in the technique index that can be applied under analysis, inspection, demonstration, and testing techniques. An example is requirement number 1 that the STCT shall be able to send a readable signal at a minimum of 150 meters. Its traceability ID is 1.1. Its category is a function of requirement, and the functional test will test the whole system during the qualification stage. The RBTM determines and assures if the STCT requirements can be traced forward to their specific subsystem, component, and element to be produced, and it also determines and assures if the STCT subsystems, components, and elements can be traced back to their specific requirement and specific IVVT method. Our RBTM identifies the STCT system, subsystems, components, verification, testing method, techniques, and each requirement and its requirement traceability ID number. An example is the same requirement we identified in the RVM slide, requirement traceability ID number 1.1. A functional testing technique method will be applied to verify that the RIFD chips are sending a readable signal at a minimum length of 150 meters to make sure the STCT system operates as intended. Here we have the STCT VVT management plan, which identifies a list of VVT activities, milestones, and reviews we will be conducting and documenting from the definition stage to the post-development stage of the STCT project. We identified the module number and the milestone stage, the activity it was conducted in, the date each activity was initiated, and the due date each activity needed to be completed by. An example is in Module 5. The built-in test was conducted during the integration stage. We initiated the test on October 18th and completed and submitted the test report by October 24th.
6.1.2 ConOps and Review. The figure is a high-level diagram that explains the operational concept of the see-through chip tracker. It demonstrates the interactions that will be performed by the components within the system and the autonomous vehicles. The chip is embedded on a US road sign. The see-through chip tracker will emit radio frequency waves, or RF. The antenna in the autonomous vehicle will pick up the RF signal. The reader will decode the data and send the uncompressed data to the autonomous vehicle's AI for the vehicle to make an educated decision. 6.1.3 System Requirements and Review. The system requirements are defined and initial defects are removed. The developed system must meet the requirements in order to consider the system successful. The categories for the requirements are functionality, communication, cost, performance, structure, testing, compliance, maintainability, reporting, security, documentation, control, traceability, and electronics. All of the defined requirements are reviewed and approved by key stakeholders for validation purposes. Although these requirements are rules the system must adhere to, these are not set in stone. Through the development cycle, some of the requirements can and have changed in order to ensure success. 6.1.4 Requirement Verification Matrix, RVM. All of the requirements have been approved and validated with key stakeholders. Now the requirements have to be verified within the system's development cycle. Depending on the type of requirement, different techniques can be used to verify each one. The techniques are analysis, inspection, demonstration, and test. The stage at which the requirement will be verified is also defined. This is crucial as some requirements will be verified in the first stage, definition. The stages are definition, design, implementation, integration, and qualification. Lastly, at what level will the requirement be verified? Component level, subsystem level, or system level?
6.2.1 System Cost, Benefit Analysis, and Risks. Cost-benefit analysis is a way of measuring the benefit of having certain functions versus the risks they bring and the costs associated with those risks. The cost-benefit analysis for the STCT was done using risk identification, probability of occurrence, and severity matrix. Probability was rated from 1 to 10, 1 being lowest and 10 being highest. Severity was also rated from 1 to 10, 1 being minor and 10 being disastrous. These values are then multiplied to obtain an overall risk value. These values can be assessed using a risk matrix to determine if the risks must be accepted or mitigated with a contingency plan. Below, the CBA for the STCT requirements is provided. You can see that most of our costs for each risk is relatively low. However, we have dedicated large sums over $250,000 to help mitigate all of our most severe risks, which had high severity, but moderate probability. For instance, risk 26 and 28, stating the chip could be hacked or it could be giving the wrong signal, could cause an accident on the road, which would be the worst case scenario. Therefore, we saw that these risks were too high for us to accept, and in order to decrease the probability of them occurring, we allocated more money to a mitigation plan for these risks. 6.2.3 Requirement Bidirectional Matrix. The RBTM is used to determine that all requirements in a product have been completely addressed and that all requirements can be traced to a valid source. The RBTM provides a mechanism to go from a requirement to its implementation, while also providing a mechanism to go back from an element in the implementation to its requirement, providing a reference. This allows review of backwards and forward traceability for each requirement. The bidirectional traceability matrix and checklist also allows you to measure alignment of design with requirements. This helps make sure that the functions are in line with your requirements and are in fact necessary, or if your requirements have been accounted for. Specifically, for the STCT, we had good balance of requirements that were backwards and forwards traceable, which will help us later in the later stages of development for verification and validation purposes. Some of our requirements were at the system level, but we chose to have them also be traceable at the component level to be more easily traceable when the time arose to verify or validate the requirements later. For backwards traceability, there are different types of testing that can and will be performed to verify compliance of requirements. In addition to testing, there are also design reviews, software manipulations, walkthroughs, and checklists to verify the requirements. All these techniques can be viewed in the second key in the previous slide describing the techniques, its category, and symbol it corresponds to. You can also see in the first key in the previous slide the different aspects of the STCT and how they're categorized in terms of system, subsystem, component, tests, and other entities.
7.3 Implementation. Component Test Plan. The System Test Plan document describes the overall testing approach for testing the battery component of the see-through chip tracker system. The primary source of reference for this test plan is the System Requirement Specification document and the Concept of Operations document. The main tests to be performed, as well as the test strategies to be implemented, have been identified and are listed. This document will serve as a guideline for the people performing the tests and inspections to evaluate the battery's performance and power specifications. The main objective is to verify that the system battery meets the technical and functional requirements. For the actual test, the STCT IVVT team developed a battery performance test with two different modes. Standalone mode, meaning with no solar panel attached, running on battery power only. For this mode, battery charge measurements were taken at 12-hour intervals until the battery was fully depleted. Time of dead was captured for each battery. And the second mode was an integrated mode with the solar panel attached. This is also the way the system is intended to run operationally, assuming sunlight is available daily. For this mode, battery charge measurements were also taken at 12-hour intervals. However, since the battery was being constantly charged by the panel, it was never fully depleted. Instead, we performed a charge measurement at the end of the 1-month test, and charge level at that time was recorded. Component interface analysis. A testing plan will be conducted to test the functionalities as well as the technical performance measures of the battery and solar panel of the see-through chip tracker system. The different test scenarios will be tested by team members that are subject matter experts and have adequate skills to operate the testing equipment for the battery component, including a multimeter and voltage meters. Interfaces between the battery and the system and the solar panel and the battery will also be tested. 7.3.3 Validation Criteria for Acceptance. Criteria for evaluating results. Our system under test performed within the specifications described in our component test document. For the batteries without the solar panel, the test was executed until battery was fully depleted. For the batteries with the solar panel attached, the test was executed for a month. Batteries without the solar panel reached 0% battery in an average of 107 hours, which is about 4.5 days. The batteries with the solar panel, however, each time the charge was measured, the voltage was between 100 and 90%, 100% during the day and 90% during the night. This is in line with the assumption that the batteries with the panel will never reach a fully depleted state because the solar panel was constantly charging the batteries. And at the end of the 1-month period, the average was 96%. In terms of peak battery, after the 1-month period, the batteries were still charging to 99.5%, still within technical specification. 7.4 Integration. Plan for integration tests. During the integration phase, we opted for creating a built-in test that would test the signal sending capability of our system. As a product whose main functionality is to send traffic signal information to passing cars, it's crucial that the STCT can accurately and consistently send signals to the receivers. Having a built-in test to verify the correct operation of this capability allows our system to detect faults and alert the user that it requires attention. Integration test description. For the integration test, 200 STCTs will be used in a remote area on post to simulate its use in regular weather conditions. 100 of the STCTs will not have the solar panel component, while the other 100 will have the solar panel component to charge the battery. This test will continue to run for 1 month. Expected results from the test should indicate that the STCT can perform nominally for at least 72 hours without the use of a solar panel and be able to hold 90% to 100% charge for the entirety of the test with the solar panel. Each test case and its results shall be recorded with a table with the average times being recorded for the STCT with and without the solar panel. Another similar table will be used to record final charges for the STCTs with the solar panel. Built-in test. The STCT has a capability to send out a signal to the local DOT office every hour, giving whether the all clear signal or error signal. The bit we developed tests this capability. Each STCT will be fully operational and be modeled as the final product of the system to achieve the closest conditions possible. 10 of the STCTs will have an error force upon them in order to check for error status. The procedure will take place as follows. We start with 100 STCTs in the operating environment. We install a central reading device for STCTs to receive and send signal information to. We ensure all STCTs are in working conditions and charge at 100%. Check received signals in the central reading device. We then force 10 STCTs to throw an error signal and monitor status. We leave the STCTs to run continuously 24 hours a day, 7 days a week for 1 month. And for recording, each test case and its results shall be recorded with a table with STCT number, signal status of all clear, or error and verification status with a percentage of correct verifications.
Post-development IVVT 8.1 Production. During the production stage, the see-through chip tracker subsystems and components are produced and manufactured. Some components may be more feasible to procure through a third-party supplier rather than manufacture in-house, such as the battery, enclosure, and maybe the antenna. Coordination between the RFID manufacturing plant and US road sign manufacturers will be required to install the see-through chip tracker onto the road sign before road installation. At this point, each embedded RFID will have to pass a small test to ensure accuracy and functionality.
Section 8.2 Maintenance. Almost every system requires maintenance, but the type of maintenance is based off of the type of system and its requirements. For different types of requirements or systems, there are different types of maintenance, which include corrective, emergency, perfective, adaptive, and preventative maintenance. System maintenance goals include minimizing the overall system cost by means of maintenance, repairing everything as quickly and as cheaply as possible, and optimizing the repair/replace strategy to save time or money. As for the STCT, it will require both corrective and preventative maintenance. With corrective maintenance, you want to make sure that you are efficient to avoid driving up failure costs due to late maintenance. The STCT will have measures to identify when it needs maintenance and minimize the downtime, which is through error codes that will be sent to the nearest DOT office. For example, requirements 9.1, 9.2, 10.2, and 13.1 state error messages that will be sent for a specific reason in order to track them more efficiently and in the meantime it'll be put in an idle state. According to one of these, the STCT will be sending an all clear signal or an error signal every hour so that the DOT will know in hourly intervals whether it is okay or not. It'll test itself once an hour during normal functioning to send out either signal, and the STCT will be monitored accordingly. If there ever were to be an instance where the DOT office was to receive an error message from the chip, maintenance would have to be performed in order to diagnose and fix the issue. Although until we receive those messages, corrective maintenance will not be needed. On this slide, we can see more requirements that will keep track of maintenance and help with performing some of these some of these requirements. Also, requirements 8.1 and 8.2 under maintainability have and will utilize preventative maintenance procedures for any other issues that we may encounter. The STCT will have foreseeable charge issues, for instance, due to weather conditions. Therefore, maintenance and proper planning will need to be developed to take care of these issues and clean the solar panels as reflected on the maintainability requirement 8.2, that the STCT shall be maintained and dusted off every 6 months.
Moving on to the disposal phase. The purpose of the disposal phase is to properly dispose of the system and its elements upon completion of its useful life. We estimate that the lifetime of one STCT should last around 10 years based on the life of the battery. Our basic disposal plan includes identifying major components of the system, breaking down the STCT into separate components, identifying whether the components will be recycled, upgraded, or disposed, and ensuring proper disposal methods are met. So our team identified the major components of the system as the active RFID chip, the lithium-ion battery, the antenna, the solar panel, the enclosure, and the RAM. Each of these components can be separated and then disposed of in a predetermined manner. As mentioned in the previous slide, there are predetermined disposal methods for each of the separate components in the system. Components can either be recycled, upgraded, or disposed of. For the STCT, we decided that the lithium-ion battery, enclosure, and RFID chip could be recycled as the metal parts that they are made of could be useful for other new components. We also decided to upgrade the solar panel and the RAM as they are components that can be easily replaced in a new STCT. The old components could also be recycled for their metal parts. Finally, we decided that the antenna could be disposed of as there is not much useful material to be recycled. However, it could be switched to the upgrade category if needed. Our team identified an appropriate disposal strategy and plan for the STCT. We needed to verify that there is no further practical use for the system and that the system end-use scenarios comprise economic value. These verifications would generally come when error signals were thrown and it was discovered that the STCT had been compromised in some way. For our case, we need to consider sensitive or confidential data stored within electronic equipment that must be permanently erased or destroyed before transferring the system for reuse or disposal. Electronic media used by the STCT is the RFID chips, which can include possible sensitive information depending on the location that the STCT will be used in, i.e. military bases. Because of this, our destruction method includes recycling the STCT by melting or pulverizing it. In summary, the purpose of the STCT VVT plan is to focus on improving how autonomous vehicles interact with the world around them through a well-established methodology of systems verification, validation, and testing. The appropriate execution of the VVT activities will contribute to the anticipated increase in efficiency and safety of autonomous driving across the United States and eventually the world. The IVVT plan is applied from the ground up, from components, subsystems, and top-level systems. These include the battery, solar panel, charging system, enclosure, antenna, and RFID chip. Compliance to certain requirements were applied and verified at different stages of the product life cycle: definition, design, implementation, integration, and qualification, due to the nature of the need for these requirements. In terms of lessons learned, as the product evolved and more characteristics were considered, some of the initial requirements were updated, rewritten, or even removed, along with new requirements being added. These changes had to be evaluated for the time and cost impact it would have on the IVVT plan and how it affected the product itself. The further progress on the product life cycle stages, less critical changes were made as the impact greatly increased due to all previous work done and the time it would take to realign to the new requirement. Of course, an evaluation was performed as far as the criticality of the requirement and the need to have it. Performance, functionality, integration testing yielded mostly expected results, and no major changes were derived from the failures encountered. This is due to no failures affecting all units, meaning that it was no design error, but issues with an individual asset. The tests were harsh and thorough, but it is to ensure the system does meet the environmental requirements, as it will not be exposed to a single climate, but all climates found within the United States.